All right. Hello, class. I'm expecting that very, very few people will probably watch this lesson because I think that most of you are probably still asleep, or at least very few of you will watch it live. Um, so I apologize. We're having a staff meeting at 1, and so I had to get my lessons in before then. Um, I had an idea for a short story last night. Maybe you'd like to hear about it. It's The idea is you know how we have vegans who don't want to use animal products because, and one of the reasons is that they think it's unethical to, treat animals. Uh, it's cruel to animals. Um, so in the short story, um, it would be about people decide that plants have feelings, and they decide they don't want to eat plants either because they don't want plants to be abused by humans. So basically, these people are like super vegans, and they just decide to not eat, and then they all just starve, and that's the short story. So, and then they have their own organization. So I'm still working out the details, obviously, but they have their own organization um, that's sort of analogous to PETA. So PETA is People for the Ethical Treatment of Animals, and I think that's what it stands for. And so these people would have CLAP, which is Citizens for the Liberation of All Plants. So, and it would be funny because when you say someone has the clap, that's an STD. So it's like the clap. Okay. So, anyways, that was my idea. It would be a satire. Um, oh, hello everyone. 11 of you. Hey Vicky. Hey, Matthew. Hey Sebastian. All right, so let's get into today's lesson. I've got 4 pages from the workbook. Remember, you are going to be submitting your workbook pages next week, and that'll be your quiz. So you're not going to get. I'm just going to check it off that you did the 4 pages. So the correctness does not matter for next week. Okay. So we've got Angela. Angela's back for this workbook page. And Angela is shaking her hand left and right on a rope to get a continuous wave. A graph of a continuous wave is shown at the right. So notice how we have a y versus x graph, not a y versus t graph. So this is a displacement position graph. So from this graph we can get wavelength, but we can't get the period because time isn't on the horizontal axis. By the way, we're doing waves today. And then next week we're going to go back to stuff from first semester. Let's see. On the diagram, label a crest, a trough, an amplitude, and a wavelength. So that's pretty straightforward. An amplitude would be this distance right here, whatever that distance is. Okay. So that would be an amplitude. A wavelength would be this distance right here. It's the distance between 2 crests or 2 troughs. That's not very precise. If I wanted to make it precise, it would be here to here. So notice how we can move this around. This is also a wavelength. This is also a wavelength. So, there are lots of different ways to measure a wavelength. Also with amplitude, notice how we can choose any peak we want to, or we could even choose a trough because it's symmetrical. And then we want to label a crest. A crest is the highest point of a transverse wave, so that would be a crest. And then a trough is the lowest point of a transverse wave, so that would be a trough. All right. Part B, on the diagram below, sketch a continuous wave with half the amplitude as Angela shaking her hand back and forth 5 times per second. The wavelength is 1 meter. Calculate the speed of the wave. So half the amplitude means it looks like this wave goes up 1, 2, 3, 4, 5 blocks. So a wave with half the amplitude would go up 2.5 blocks. So let me draw that. Half the amplitude. So I'm just using this as a reference for when I draw it. So then I draw it like this. Something like that, half the amplitude. Okay. Then it also wants us to calculate the speed of the wave. So notice how it says that Angela is shaking her hand back and forth 5 times per second. So that means that 1 full period, you can highlight that. That means that 1 full period is going to be equal to 0.2 seconds. Okay? So why is that? That is because if you are waving your hand back and forth 5 times per second, you have 1/5 of a second for a single back and forth. So that, and then the frequency is 1 over the period. So that means that the frequency is 5 hertz. And then we use V equals lambda times F to get the speed. It says that the wavelength is 1 meter, so we have V equals 1. So that means that a crest takes twice as long, so it would be something that goes like this. There's a crest. See how the crest is twice as wide, and then the trough is twice as wide. So something like that. Part D says, is Angela shaking the string at the same rate? I would say that Angela is shaking her hand slower. Why do I say that? Well, I would say the speed of a wave is determined by the medium. Which didn't change. Okay? So the wave speed is still going to be the 5 meters per second we calculated above. Okay? So frequency equals V over lambda. Okay? So we can see that if lambda goes up for a fixed wave speed, the frequency goes down. So that means that Angela is shaking her hand more slowly. All right? Let me check if anyone has questions about that. Hey, Charlotte. Hey, Will. Thanks for joining us. Okay, going on to the oscillator has a display that indicates the frequency. You are asked to design an experiment to determine the velocity of standing waves on the string. Okay. So, this is an experiment. I actually mentioned this experiment. This was an experiment that I mentioned last week, I believe. Okay. So what we want to do is we want to set up a table. Okay. And right here is your oscillator. So this is the oscillator. So what an oscillator is a thing that shakes at a frequency that the user can control. So you turn a dial and it shakes more quickly or less quickly. So and then it displays how often it's shaking. Then you have a pulley. Okay. And you have the rope. You have a rope that's going over the pulley. Oops. Like that. And at the end of the rope is a mass. Kind of like that. So this is a mass. Oops. Okay. So basically what's going to happen is the mass sets the tension. Sets the tension. And then what you do is you would measure L, the distance from measure L, the distance from the oscillator to the pulley. Okay. Then slowly turn up the oscillator frequency. Eventually, the first harmonic of a closed standing wave will appear. Okay, so record the frequency. So eventually you will get the wave that looks like this, remember? So that's called the first harmonic. So then what you would do is you would continue raising the frequency until the second harmonic appears. Record this frequency. Continue. So that would be my procedure, something like that. Of course, the second harmonic is the standing wave that looks like so. Like that. So how would you analyze your data to determine the velocity of waves on a string? Well, we know that the frequency of the nth harmonic is NV over 2L. That's for a closed instrument. We have a data table of frequency versus harmonic number, right? Because we basically turned up the frequency until we got to the next harmonic, then we record the frequency, and we keep turning up the frequency until we get to the next harmonic, record it, etc. So we have frequency versus harmonic number as our data table. Graph frequency versus harmonic number and find the slope. You always want to relate it back to the slope of the graph. Okay, the slope of the graph is the thing that's going to tell you something. So we can see that F equals V over 2L times N. So the slope of the graph is V over 2L. We measured L and found the slope, so we can solve for V. That's what I would do, something along those lines. You could even do something where you like change the length of the string. You could change the length if you wanted to. There's all kinds. So you could find the first harmonic every time, but then change the length of the string each time. So you would always have the first harmonic, but then you would be changing L. So there's lots of different ways to do this. I wouldn't change the mass, though, because if we change the mass, that's going to change the tension in the string, which is going to change the wave speed. Okay? A student performs the experiment and collects the following data. Okay. Fill in the sketch column with what you would expect the wave to look like. So we have the first harmonic, which looks like this. We got the second harmonic, which looks like this. We got the third harmonic that looks like this. Whoop. What happened there? Remember, you add a football each time you go to the next harmonic. Fourth harmonic looks like that. Oh, and they did the eighth harmonic. All right. So that's going to look like two of the fourth harmonics end to end. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, okay. Graph the necessary data to solve for the speed of sound. So based on, so you remember how I said that the slope is V over 2L? So what I would do is I would notice that the second harmonic is going to be the length of the string. So based on this, I can conclude that L equals 1 meter. That was the L value for this experiment. So it looks like for the first harmonic, so I have a graph here, and here I have harmonic number, and here I have frequency. That. And so here's the first harmonic, with, we can see that the first harmonic has n equals 1 and a frequency of 100, okay? The second harmonic has a frequency of 200, so the second harmonic would be this data point right here. So notice how each block is one harmonic number on the horizontal axis and 100 hertz on the vertical axis. And then the third one is 300 hertz. The fourth one is 400 hertz. And the eighth one is 800 hertz. So that's the data. And then we draw our line of best fit. It goes like that. So what we notice is that the slope of the line went over it went over 8 harmonics, and it went up 800 hertz. So the slope is 800 divided by 8 equals 100 is the slope. And in the procedure, we said that the slope was going to be v over 2L. So that equals v over 2 because the length is 1 meter. We determined that already. So that says that v equals 200 meters per second. All right. Part F. Argumentation. Let me check for questions. Are we allowed to draw diagrams on the AP exam? Excellent question. Now if you were to take the AP exam under normal conditions, I would say absolutely you can draw diagrams. I don't know what they're going to do this year. In fact, I was just talking to Simon about this yesterday. So I would expect probably this AP exam is going to have mostly typed answers. And the reason that I say that is because it's designed to be taken on a computer or on a phone, or they said that people could take the AP exam on the phone. And I don't know how someone is going to be able to type in equations or draw diagrams on the phone. So I would expect that most of the answers are going to be, or most of the questions you're just going to type an answer. Garrett has a question. He says that this isn't related to the video, but this week's AP1 quiz looks like it is missing from the actual doc. Garrett, I think it might be just you. I would probably pull down on because I've been getting, people have already sent me their quiz, so I think that the quiz is working. What I would do is I would refresh the folder because maybe the updates to the file haven't transferred to your particular copy of the folder. Okay, so going back to this, we got some argumentation. These drawings represent snapshots taken of waves traveling to the right along strings. The grids in the background are identical. The waves all have the same speed, but their amplitudes and wavelengths vary. Rank the frequency of the waves and explain your ranking. Okay, so they all have the same speed. They all have the same speed. We know that frequency equals v over lambda. So only lambda determines the frequency because they all have the same speed. Notice that the amplitude has no bearing on the speed or on the frequency. because this equation doesn't have A in it. So we can see that shortest wavelength has the highest frequency. So that's going to motivate the ranking. And so it looks like the, so let me find the wavelength of each of these. So the wavelength of A would be from here to here. So how many blocks is that? 1, 2, 3, 4, 5, 6, 7, 8. So this one has a wavelength of 8. So A has a wavelength of 8. I can also see that B has a wavelength of 4. I can see that C is a little bit tricky because here's the highest point and here's the center line. So that highest point to center line is 1, 2, 3, 4, 5, 6. But that's only a quarter of a wave. So that means that C actually has a wavelength of 24. Okay? And then by the same logic, I can see that D has a wavelength of 16 blocks. So that makes it easy to rank them. So that would tell me that the frequency of B is the greatest, then the frequency of A, then the frequency of D, then the frequency of C. All right? So I think that's it. What was the last page I was going to do? Let me check. Last page I was going to do was 285. I just did page 285. So that's all my questions for today. Hello, Jaden. So thank you for watching. I appreciate you waking up and showing up, and those of you who are still working to trying your best to learn. I really appreciate it. Good job, and I hope you guys are all doing well and have a great weekend. Bye now.